Recording.
Good. All right. This is the last portion of this section, right? This lesson is the last bit that we're going to see about independent events. From here on out, we're going to have dependent events. We're going to have conditional events. We're going to have sequential things that happen. And we'll learn how to get the probability of all those. But today, the basic thing is you're asking, is it an independent event? And can I test if it's an independent event? I'm going to have a lot of examples up here. We'll go through one at a time. And this is stuff that you already know. So you already know that independent events, one event has no effect on the other. So there's no magic in this coin. If I flip it once and can't do it, if I try twice, I'm flipping it once. We got a heads. Okay, did that heads have anything to do with my next flip? Nothing, right? So sometimes, just anecdotally, you can think and see, is there magic? Is there magic that, the next one will be tails because that was heads, or vice versa? No. So flipping one coin is like a basic example of it's an independent event. Each flip is independent. Okay. There's going to be scenarios that it's not as, like rolling a die. If I roll this die, flip the die, and I get a 5. Does the 5 tell the next roll, hey, don't get a 5, that'd be embarrassing? No. That kind of works. 3. So different. It doesn't matter though, right? There's no magic between it. So I'd say even with that, independent events, there's no magic involved, right? There's no magic. All right. You won't always be able to see it so clear cut. There's going to be examples, especially moving forward. It's going to get a bit more complex as we go through the weeks. You'll use the independent event test to prove it for sure. Because I feel like everybody can make an argument for one coin is independent, but if you have to prove it to me, show me. You'd use this right here. And we'll look at that in a second. Let's go to the new stuff.
Got it.
Yeah, okay. It's like one of those little dollars on the string. I see. So this is new. Dependent events affect each other. So let's look at that together. And get out your placards. Let's look at this. Because we have the placards up here. Let me make sure I can see. Okay, kind of can see. Great. Now, what would you say the probability of picking a, picking a diamond? What's the probability? All those would satisfy that event. Would you agree?
Yes.
To pick a diamond, we have 13 of the 52, which is 1/4. Just making the best of every wrong number. But what happens here? All right. Let's see if Caden's feeling lucky. Try to get a diamond. So he's got a good chance. 1 in 4 ain't bad.
This is a diamond.
Is a diamond.
Nah.
It's the King of Hearts. Oh, man. All right, so we got the King of Hearts. Let's put that on the King of Hearts. And here's the thing. Before, we were putting all the cards back in there, right? And so the odds every single time, it was independent. It was 1 out of 52 every single time. But here's the thing. Now this king is on here. So now what is the probability of getting a diamond? We've discarded.
51.
Good. Discarded 1 card. So the resulting, there's still 13 that we want. The top number isn't going to change with dependent events. The bottom number is, and this actually, instead of 0.25, 25%, this ends up being more like 0.254 or something. 25.4%. So tell your neighbor why our odds got better. Why did the odds get better? Just tell your neighbor, 5 seconds.
They took the card.
Okay. All right. Yes, say that really clear and loud for everybody. What happened?
Sample space got smaller.
Good. The sample space got smaller. I know that the denominator is always the total number of options. The total number of options shrunk. So let's say that the next cards I pull are this one, and that one, and then I forgot what game I was playing. I didn't even count it. but I actually picked a diamond and forgot that I was looking for diamonds. But then after I did that, now I'm like, oh yeah, what the heck am I looking for? I'm still going to do it. All right. So now this card as well has been discarded. I want you to find the probability of getting a diamond when these have been discarded and I made a mistake. I didn't count that that was a diamond. So this is just as if it's another discarded card. That card is not going to be from what I can draw. So I want you to find then, again, in this case, the desired has a change and the sample space has a change. So I would do that too. All right, so what is that? What is that going to be? 1, 12 out of 48. How many cards have been discarded? How many cards have been discarded? 1, 2, 3, 4, 5, 6, 7. So 52, it's no longer 52. We have 7 out of the sample space taken out. So how many are there? 45. Because there's 45 options up there. I can get this one, 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 this one. I can't get that. I can't get that, or that. So what is my desired as far as the set? How many items are in my set of desired values? Still trying to find the probability of diamonds in this scenario. 12. Because I forgot what game I was playing. The 4 was picked and I forgot. Okay. So 12 out of 45. And that's going to be, give me a decimal. So we have about a 26.6% chance now. Okay. So if I were to go through this and somehow I picked, we could find this probability, but we won't. I picked all the cards except for, even this one's back in play. All the cards except for a diamond. And I had 13 cards in my hand. What would the probability be of getting a diamond? 100%. So you see that if you start discarding cards, as you discard more and more and more and more, if you got through all the top 3 rows, you had the bottom row, then you have a 100% chance because every card would satisfy it. Okay. Thumbs up, sideways, down for seeing it? Okay, good. Let's keep going. Yeah? Good. All right, let's look at this over here. Going back. Whoops. All right, so let's take this card back. Nah, we don't need that up. Whoops. Keep kicking stuff. There we go. All right, we're back. This actually was part of the scenario, so we are going to look at this quickly. Maybe this is just a quick note. We knew that this was 1/4 chance to get a diamond. If I picked an 8 and then discarded it, I would then have 13 out of how many was it? 51. Okay. Which I think we got was 0.254, which is equal to 25.4. Everyone good with that first part? Good. Okay. Now we get into some things here that are going to take a little more thought. Independent event. We're going to always assume that it is an independent event and test it. So even if we can tell, if we were to do this scenario out with discards, we would not be able to pass this test. You know it passes when what's on the left and the right, these combine and they're equal to each other. The same value is on the left and right. Okay, so let's see. It's basically like this. We're testing it, so we say this. I don't know. We're going to see if it's equal. If it is equal, then it is independent. Okay. So if we look at this, let's look at our events. We'll do them on our cards. So I want everybody to do this on the cards. What is event A? Draw a heart. Event B, draw an 8. So pick an 8, pick a heart. Let's go ahead and see if we can get that set up on our chart. This actually, the chart is going to help you see this. So let's go ahead and everybody knock out that chart. All right, so draw a heart. All those. Right. Draw an 8. How many cards fulfill that? 4. Got that 8, that 8, that 8, and that 8. And what is the intersection? How many cards are in the intersection of that? 1. So I'm going to put an intersection note on that one. So it'll The upside down U, remember, is intersection. U is union. Okay. So let's look and see what we have here. We have our two events. A is get a heart. B is get an 8. So we have that listed out here. I'm going to rewrite it right here. So the probability of A intersecting B is equal to A probability times B probability. This is our addition, our independent event test. Now, you may look at this and be like, how the heck are we going to find the probability of the intersection of event A and event B? All this is saying is that the choice you want satisfies A and satisfies B. How many cards satisfy A and satisfy B? One card. It's the intersection card. It's this one right here, 8 of hearts. So watch. It's 1 out of how many cards? 52 is equal to, what is the probability of drawing a heart? A heart? We get 13 out of? 13 out of 52 is 1/4. So the probability of A, of getting a heart, versus getting an 8, the probability of getting a heart is 1/4. What is the probability of getting an 8? 4 in? 4 out of 52. So I like to reduce all my fractions as much as I can. So I'm going to divide this, and that's going to be 1/13. Okay. So now I have to check. 1/52, is that equal to 1/4 times 1/13? Okay. Remember, with multiplication, we multiply straight across, so that's why this independent event test is pretty quick to do. 1 times 1, 1. 4 times 13, 52. Did this match? Did the product of these two probabilities match the product of the intersection of those two? They did, right? So what do we know? Is it independent or dependent? Independent. If it passes, it's independent. Okay. All right. Not bad. Can we do it? All right. How about this? I'm going to show you how, even if it gets more complicated, we can do these problems. I'm going to make A drawing a spade. I'm going to say B is drawing any numbers 1, let's go ace through 4. Ace through 4. So I have to move this so that we can write it. I want you to go ahead and fill in first A, and then let's see if we can do B. Okay. I have this example and then 2 others I want to do. So let's try to do this quickly. If you're daydreaming, bring it back quick. We're going to go ahead and mark all the cards that satisfy A. And why don't we get the probability of A while we have that? What is the probability of A? What is it? 13 of the 52, 1/4. 1/4 of the suits. There's 4 suits. It's 1 of the suits. How about that probability of getting A through 4? Let's see. We got to, this is just, sorry, probability of B, which is A through 4. We got to list all those out, right? So we have, we have this one, this one, this one, this one. You can make dots, you can circle them, you can fill them in, whatever you want. All right, how many is it? 16 out of? 16 out of 52. So let's now look at what is the probability of the intersection of A and B. How many satisfied being a spade and satisfied being ace through 4? 4 cards. Go ahead and circle them on your chart. All right. We're going to be able to do this quick. Probability of A intersection B is 4 out of 52. So that's 1/13. 4 out of 52 reduces to 1/13. The probability of A was 1/4. The probability of B, 16, so that's 1/13 as well. Yeah. Let's see. Is 1/13 times 1/4 going to be equal 1/13? What? Which one are you talking about? I'm confused. 4/13. Yeah, Caitlin. Thank you. Thank you. Great. Multiply straight across. Multiply straight across. We get 4. 50 seconds, which equals 1/13. So, does it pass the independent event test? Yes, independent. All right. So even when there's an intersection, it doesn't mean that it's going to be dependent. Next week, we talk more about dependent probability and conditional events. That's where we talk more about just the dependent component. This is just testing for independent. Thumbs up, sideways down for doing that kind of complexity. Okay, great. So we need to now go to the page in your book. Go ahead and please get open to page 34. We're going to look at example 2 first.
Wait, do we still need these?
Yeah, well, you don't, but just hold on to them, actually. You don't need them yet. All right.
I gotta go in 1 minute.
That quick, huh?
That was pretty fast.
I thought your dismissal was at 40. No?
It is, right?
Oh, jeez. All right, that works. Yeah. Okay, just watch the chords.
Yeah.
Okay. All right, we're on page 34. Page 34. All right, let's look at this. Trevor tosses a coin 3 times, so you're going to have a 1 toss, a 2 toss, and a 3 toss. So, event A, the first toss is heads. So watch. For event A, the first toss is heads. It doesn't matter what the other ones are. Second, for event B, we have the second toss is heads for event B. All right. Here we go. Good luck.
Thanks, Bucket. Hit home run.
Grand slams. Only grand slams. All right, there's exactly 2 consecutive heads. The word, anytime you see this word, exactly, you have to really think about what that means. Because does heads, and another head satisfy that? No, because it's exactly 2 consecutives. Okay, so if I look at that, I could have heads, and then what? Tails, or I can have tails, heads. You see how that's actually has like the most requirements to it. Okay. So again, it says exactly 2 consecutive heads. So I know that there could not be heads, because that wouldn't be exactly 2 consecutive heads. So heads, and then a tail has to be a tail. Tail and heads. Anybody want me to go about that, explain it again? The word consecutive, though. Consecutive is going to be they're right next to each other, the first, second, or the second, third. Now, they give us the sample space right here. Copy them down really quick. There's 8 of them. Heads, tails, heads, tails. It's going to take a moment, but we need to look at them on the sheet. If you add them, it'd be helpful. We're going to get the probabilities of each of these. All right, sample space. Give you another like 15 seconds, 10 seconds. I'll move it up. Useless. You see it now? Yeah. All right, everyone getting that? And now, somehow, I don't get exactly where it was. Let's see if I can do it. Oh, there we meet again. All right. We're going to look at our sample space and just one at a time figure the probability for each event. Okay, so let's look. How many out of 8 in my sample space, how many satisfy A, that heads came first? How many satisfy A, that heads came first? Count them. They're on your page. You can look at your page. Yeah. Heads came first. Heads came first. Heads came first. Heads came first. 1/2. Okay. The next option is out of 8 as well. And this one is, let's see, that heads came second. Let's see, how do you know? Because this is saying what the first, second, and third flips were. That was tails, heads, heads. So from that, which one of these has heads in the middle as your second roll? Let's see. First one? Second one? Whatever this one is. Fifth one? Sixth? That's it. So what is that? It's half of them. It's 4 or 8.
I'm sorry.
I missed one? No. All right, look at, we already figured out what these have to be. So how many options fulfill C? 2 out of the 8. 1/4. Okay, so again, remember, we're applying this rule right here. A intersection B, that has to be equal to probability of A times probability of B. We've done most of the work here. So we need to look now at what is the intersection of A and B. So I want you to make a arrow or circle or whatever. All of the 8 options that satisfy heads being first or heads being second. So let's see. Heads being first, heads being second. We got this one. That one. Is that it? That satisfies A and B. That heads is first, and for B, heads is second. Heads, heads. Heads, heads. Okay? Okay, I get it. Okay. So we know that for this, the A intersection B is 2 out of the 8, so that's 1/4. And let's see if that equals the probability of A we've done. 1/2 times the probability of B, 1/2. What does it equal? 1/4. So, independent, right? When they equal each other, the product equals the intersection, then we know that independent. And this is what we're trying to figure out, if it is independent for this. All right, let's see, A and C. So A is that heads came first. C, we actually already know which ones we can look at. So which one of these options for C, which one of these options also meets the requirement for A? Which one, Santana, what do you think? HHT. HHT, we know that C is only going to have these 2 different options. We figured that out before. So let's look. We have heads first, and it's just this one on top here. That's the only option that works. So we're going to put 1 out of 8, and that's going to be equal to probability of A, 1/2. The probability of C, 1/4. You multiply those. 1/8. They match? All right, I want you to try to do B on your own. Try to do B on your own. B and C, sorry. The intersection of B and C, so between these two. How many fulfill both of those requirements? B is saying that H is in the middle. You get a heads in the second flip. This for C, we have that H heads is the second one for this option and for this option from our sample space. So 2 out of the 8 meet the requirement for B and C. Right? First I look to B and I see, will the requirements for B fit inside of the requirements for C? You're seeing what fits inside. So if the second roll is heads, I know that this one works, heads and then a heads and tails and a heads and then a heads, because the heads is the middle roll right there. So there are 2 options that work. 2 out of 8, 1/4. And then we just got to multiply the probabilities. B is 1/2. And C is 1/4. Unfortunately, it gives us 1/8. So what kind of event do we have here? So it did not meet the requirement of these being the same. So we know it's dependent. That's the key. All right. And yeah, you guys are probably pretty full. There is one other example I want to do. How about I just show you and kind of strategize about it? Because thumbs up, sideways, down right now. Okay, that's what's happening. That's what I thought was happening. It's not, you guys understand what we're doing so far? Good. So we are going to just look at example 3 to give like a strategy for it. So just turn the page to example 3, or it's on the same page probably. Okay. So we are looking at this. This is a 2-way frequency table. You have 4 kinds of sandwiches at this delicatessen. You have 3 types of bread, but it's like make your own sandwich. So you can get a turkey melt that's on sourdough. You can get a roasted chicken on sourdough. You can get all these different options. Okay? So what I want you to do first for these type problems is to find the marginal frequency. The marginal are going to be the totals of all these values. So we're going to add up these. Add them up, put it here. Add them up, add them up, add them up. And then find the marginal frequencies over to the right, finding how many country white, bread loaves did they use. So this is a quick add up. Sleepy time. All right, 44 plus 48. 92, 25 plus 28 plus 27, 80. 51 plus 24, 175. Nope, 75. See if you're watching. 65 plus 8, 73. 102. Oh, you need this one too. And then we're going to have a total for all of the sandwiches over here. Total. Let's see, 24 plus 28 plus 26. So go ahead and add, just for time's sake, go ahead and add these numbers in to your margins. I just did them quickly. $106. So I think there were 320 total sandwiches. Okay? So let's check if this is independent. A random customer, we'll just do it quick. A random customer orders Landon's club sandwich on country white bread. Club sandwich, country white bread. So we have club sandwich and country white bread. Okay. Now, if we want to work this out, we're going to have the probability of, let's call this A, call that B. So the probability of A intersection B, probability of A times probability of B. All right. So what is the probability that somebody ordered a club sandwich on country white bread? There's 320 sandwiches made for the whole week. I just added together all the breads you use. You could have added together all the sandwiches. We've got 320 total. So, probability of getting country white on a club sandwich is the intersection of A and B. So this is A, that's B. So what is it? Out of 320, how many sandwiches had both those intersections? 44 out of 320. What is the probability that somebody ordered a Landon's Club sandwich? 320 is still going to be the total sample space because that's how many sandwiches were made that week. So how many club sandwiches were made that week? 92, right there. Times. Tell your neighbor what you think the probability of B is. Probability of B is country white bread. Probability that country white bread was on any sandwich in the whole week. Okay. Here's the total. How many were country white? 1 out of 2. Okay. Now this is where we'll end. Just looking at this, who's looking forward to multiplying 320 times 320 and 92 times 101, 2? You don't like that either, right? So we can assess this whole thing as decimals. So I would have you convert each of these to a decimal, multiply these, and see if you get the same answer. Okay. This ends up being, what did this end up being? It doesn't pass it, so these are dependent. All right, that's all the strategy I'll give for that one. When you have really hard fractions and you can't reduce it, or even if you can, throw them in decimals if you don't want to waste time. So we're just checking to see that they're equal on both sides. All right. So give me a thumbs up, sideways down for this lesson. How's it working? Okay, good. Hey, keep it up, and we will say goodbye. Goodbye.